Hello everyone, today we are going to see about Bessel inequality for finite cases in functional analysis. So the statement for the Bessel inequality is let E1, E2, En be the finite number of orthonormal set in the Hilbert space. Okay, if X is any vector in H, X be a it is a in Hilbert space H, there will be a finite number of orthonormal set, and X be any vector that is also present in the Hilbert space, then the summation of I equal to 1 to n modulus of x comma, that is nothing but inner product of x comma ei the whole square less than or equal to norm x square. Further, x minus summation I equal to 1 to n x comma ei into ei orthogonal to ej for each j. So we have to prove this one and this one. Okay, for that we have considered the set e1 to en be the finite orthonormal set. So the orthonormal set is nothing but if I equal to j means it will be 1, I not equal to j means it will be 0. So for the finite number of orthonormal set ei comma ej equal to 0 means I not equal to j, and ei comma ej equal to 1 means I equal to j. We have to prove this form. So we have considered that choose y equal to in the form of x minus summation I equal to 1 to n x comma ei the ei. So we know that if we take the norm, means norm is the length, so the norm is usually known as the positive value. So norm y greater than or equal to 0 for our proof. We took, because here is based on the square value, so we took norm y square is greater than or equal to 0. So instead of y we have to replace x minus summation I equal to 1 to n x comma ei, so the whole square greater than or equal to 0. For simplification we choose x comma ei as ci. So if we choose ci means we get a norm of x minus summation I equal to 1 to n ci ei the whole square greater than 0. So the norm x square can be written as x comma x. Okay, like that we wrote x term and another x terms greater than or equal to 0. And if we cross multiply means if we multiply means x comma x, then minus this term into x and this term into x into this term and this into this. So if for our differentiation, if it is present in the first form means it will be I, and if it is present in the second form means it will be j. So this is I and j. So if we take this is as usual, and in the fourth term we took ci from the, yes, this is nothing but x comma x and summation term into x and this term into x, and this is summation terms usually outside. And if we take, which means alpha x plus y means alpha x comma y. If it is x comma alpha y means we wrote alpha bar of x comma y. So it is first we take this term means ci is usually present in the first order, so it is ci, and cj is present in the second term, so it is cj bar into the left term is ei comma ej greater than or equal to 0. So it is a orthonormal set, so usually it I and j will be equal, so it goes to 1. Okay, the left terms are written here. In the last terms with respect to j, finite terms will be then x comma x is norm x square, and this term is if we take ci from this inner product means summation I equal to 1 ci ei comma x, and this is summation j equal to 1 cj x comma ej plus summation terms, both the summation terms, and ci comma cj bar greater than or equal to 1. We know that we choose ci equal to x comma ei, and ci bar is nothing but the reverse term. Ci bar is nothing but ei comma x. Cj is x comma ej. Reverse term is ej comma x. So what we do means in both the case it will come as in both the terms it will come as c like this. So both ci and ci equal to j. Okay, so I equal to j means this term crossed out, and the left of the term is nothing but this term and this term. So only we wrote this norm x square minus summation j equal to 1 to n c j c j bar holds c j bar greater than or equal to 0. And we know that z z bar equal to norm z square modulus of z square, so it is cj square greater than or equal to 0. Cj is nothing but cj, what is our cj? X comma ej, so it is modulus of x comma ej. And this is greater than, but we have to prove this. So taking this term this side means j equal to 1 to n x comma ej the whole square less than or equal to norm x square. Both I equal to j, instead of j we replace I means we get this term. Hope you all understand. Further, what we do means it is orthogonal. We have to prove it's orthogonal. If z not orthogonal to m means this is nothing but z not comma x equal to 0. Okay, for that condition we took x z not as x minus summation I equal to 1 to x comma ej comma ej, that is orthogonal term is ej, so it will be equal to 0. So instead of that we substitute my each terms, so x comma ej and summation I equal to 1 to n x comma ei the whole ei comma ei. This will be what will be become as this x comma ej, and this term as it is ei comma ej. We already know that I equal to j, so it will be 1. And for each j or each I, um, we know that exi, which means nothing but ei into ei is 1. So left of the term is x comma ej. Okay, it will won't work. Ei is 1. So x comma ej for each j it will be 0. So both terms are getting cancelled. It will be 0. So this term equal to 0 means this term orthogonal to ej. Hope you all understand, and thank you.